Hi everyone. In this video, I'd like to introduce three binary response models: the linear probability model, the logit model, and the probit model. These models are widely used in empirical research and will be useful in your future studies. I will cover the theoretical frameworks of these models, how to estimate landing by Stata, and their applications in financial studies. So let's get started. The first model is the linear probability model. The linear probability model is the simplest way to model response probability. It has the form of beta 1 plus beta 2 x2 plus beta k sk. It assumes that the probability is the function of a set of linear factors x. Please note that it is very similar to our ordinary regressions we have studied before, but the only difference is that the dependent variables takes value of 1 or 0. And we can use the OLS to consistently estimate beta. And if the conditional mean is truly x beta, the OLS estimator is unbiased. Please note that the boldface later, like xit, denotes vector or matrix. And the variance of this model is x beta times 1 minus x beta. You can think of this term as the variance of Bernoulli distribution. The x beta is the probability of success, while the 1 minus x beta is the probability of failure. So as you can see, the variance is totally depends on the int, so it is a heteroscedasticity variance. So you should make sure that the OLS estimator should be made robust to heteroscedasticity. And the YIT is binary, so it is not a normal variable, obviously. So we must rely on the large sample properties to make it become an asymptotically normal distribution. And also, the estimated coefficients give a direct estimate of the effects of each xjt on the response probability. As you can see, the beta j is the first derivative of p over xj, so it gives the marginal effects of xj on the response probability. And also, we can modify the linear probability model into a nonlinear one, which includes the quadratic or interaction terms. So it is easy to do so. The linear probability model is simple to estimate and interpret. However, there are several drawbacks. The first one is that there is nothing guarantees the OLS fit values y hat to be in the unit interval. That is, the estimated probabilities were above 1 or negative. The second one is that it is difficult to impose diminishing effects of the xjt on the response probability, because the response probability is equal to x beta, so this term will increase by beta constantly. So it will be difficult to model the diminishing effects in the linear probability model. The third one is the heteroscedasticity. Sometimes we will want to use the weighted least squares to increase our efficiency. The efficient weight of the weighted least squares is equal to 1 over x beta hat times 1 minus x beta hat. However, the x beta hat are not guaranteed to be in the unit interval, so our efficient weights will be larger than 1 or smaller than 0. So it will cause a problem in the weighted least squares. However, the weighted least squares are hardly seems-worthy because we can use the usual heteroscedasticity robust inference for the OLS. But anyway, we should make sure that the estimates of linear probability models are robust to heteroscedasticity. Next, we will introduce index models, which include the probit and the logit model. The main difference between the linear probability model and the index model is that index model that employs a g function here. This g function has a domain between 0 and 1, which can make sure that your values are between 0 and 1. And in most cases, the g function is actually a cumulative distribution function for a continuous random variable with density lowercase g. And also the g function is actually increasing. If you use the probit model, then the g function is actually a normal distribution. If you use the logit model, the g function is a lambda function, which is defined as the exponential z over 1 plus exponential z. The simplest way to estimate probit or logit model is using maximum likelihood function. As you can see, the log likelihood function is like this, which is the linear combination of 1 minus y and y with the successful probability g and unsuccessful probability 1 minus g. And you can take a partial derivative with respect to beta and let it to be 0. And you can solve for betas that maximize the log likelihood function and get a beta estimator. And the consistency follows from general pool MLE results. So we need a sandwich estimator to account for serial correlation. That is, to make it robust. So how about the partial effects of logit and probit model? Well, actually, you can just take a partial derivative with respect to xj directly and get this term as the beta j times lowercase g of x beta. If you use the probit model, and the lowercase g function is actually the normal distribution density. If you use the logit model, then the lowercase g function is the exponential z over 1 plus exponential z squared. And the main difference of partial effects between index model and the linear probability model is that the index model's magnitude depends on the lowercase g function. So it is meaningless to compare the partial effects between the linear probability model and the index model. And for the probit model, the largest value of the scale factor g x beta is about 0.4, and for the logit model, it is 0.25. If we calculate the ratio of two partial effects directly, then we can get the ratio of two beta coefficients, like this, the beta j over beta h. Please note that this term is totally independent of lowercase g function and x. But in any case, we would like the magnitude of the effects, not just the ratio of the two beta coefficients. There are two common summary measures for the logit and probit model, which are the partial effects at the averages PEAs and the average partial effects APEs. The estimated PEA is defined as this, which is the beta j hat times lowercase g function of x bar times beta hat. Please note that this term is just to plug the mean values of x into the estimated partial effects function. The estimated APE can be calculated by averaging all partial effects across all observations. This is more attractive because we are averaging partial effects for actual units. This term can be further averaged across T if we desire to get a single scale factor. And when we use the PEA or APE, the scale factor multiplying beta j hat is below 1 and sometimes well below 1. And it is meaningless to compare magnitude of coefficients across probit logit and the linear probability model. Comparing the APEs is preferred and more meaningful. And if gamma j hat is the linear regression coefficients on the xjt from estimating a linear probability model, and it can be compared with APE hat directly. If you use this data, and its mfx command can report at PEA, and its margeff command can report at APE. For a discrete SK variable, the estimated PEA is like this. It is just the difference between the g function that includes the beta k hat and the g function that is without the beta k hat. And also, for binary SK variable, the estimated APE is like this. This is the average of the difference between the g function that includes the beta k hat and the g function that is without the beta k hat. Next, we will study an example by using this data. This example is the married women's labor force participation decision by using the data from Moore's 1987 econometrica papers. The dependent variable is INLF, which is denoted as the in the labor force. This variable takes a value at 0 and 1. And the control variables are the NWIFEINC, which is the non-wife income, and is calculated as the family income minus wage times hours and divided by 1,000. And EDUC is the years of schooling. EXPR is the actual labor market experience. EXPR-SQ is the square value of EXPR. And AGE is women's age in years. And KIDSLT6 is the number of kids lower than 6 years old. And the KIDSGE6 is the number of kids between the 6 and the 18 years old. But first, we estimate the linear probability model by OLS. So we regress the INLF variable on a set of control variables. And we should also make sure that our standard errors are robust. And the estimation results are as follows. As you can see, the higher the non-wife income, the higher the wage of a woman, and the higher the number of kids less than 6 years old, will decrease the women's labor force participation. Next, we estimate a cell model with probit regression. So here we change the reg command into the probit command in the Stata. And the estimation results are as follows. Please note that the probit coefficients are not partial effects, so we cannot compare this with the linear probability model. We also estimate the PEA by the mfx command, and the estimation results are as follows. Next, we estimate the APE by margeff command, and the estimation results are as follows. As you can see, the coefficients are very close to those in the linear probability model, so the linear probability model is a good approximation of probability. We also estimate a SAM model with logit regression and get the APEs as follows. And again, the APEs are very close to those in linear probability model and the probit model. If we suspect that some variables in probability model are subjected to endogenous probit, how to deal with it? Well, for this case, we have the model like this. Y2 is an endogenous variable we want to deal with. Z1 has all exogenous variables in the model. But this model can also be written as an indicator function of alpha 1 y2 plus z1 delta 1 plus u1. But this function takes the value of 1 only when the argument is larger than 0. and U1 is the arrow turn, which follows the normal distribution of 0, 1. Z is the vector of all exogenous variables, which includes the exogenous variables in the original model. We can adopt the reverse Von two-step approach to deal with endogeneity. The first step is to run the OLS regression of Y2 on Z to obtain the residuals V2 hat. The second step is to run the probit regression of Y1 on Z1, Y2, and V2 hat to estimate the scale coefficients. And finally, we can conduct the t-test on the coefficient of V2 hat to test if it is equal to 0. If it is equal to 0, then there is no endogeneity problem. If it is not, then the endogeneity problem exists. Let's see an example of women's labor force participation decisions. Here we suspect that the non-wife income is endogenous. So we use a husband's education as an instrumental variable for non-wife income. The husband's education is a good predictor of other sources of income, because the higher the husband's education, the higher the non-wife income. And also, the husband's education have no correlation to arrow turn in women's labor force participation model. The first step, we run the regression of non-wife income on the husband's education and other exogenous variables. And estimation results are as follows. And we estimate the reverse Von residuals as a V2 hat, which is the residual of these models. And also, we can estimate the linear probability model by the IV regression. We use the IVREG regression of INLF on the education and other control variables, and also use the husband's education as instrumental variables, and make the standard errors to be robust. And estimation results are as follows. In the second step of the reverse Von approach, we run the probit regression of INLF on a set of control variables and the V2 hat. The V2 hat is the residuals in the third step regression, and the estimation results are as follows. As you can see, the p-value of the V2 hat is 0.158, which reveals that there is some sort of endogeneity problem, but it's not too strong. And then we use the MARGEFF command to estimate the APE. As you can see, these coefficients are very close to those in the IV regression. So it shows that a linear probability model is a good approximation in this case. We can also use the IV probit command in Stata with a set of instrumental variables. As you can see, the command of IV probit is very similar to those in the IV regression. But here we use the husband's education as our instrumental variables, and the estimation results are as follows. What about if endogenous variable is not continuous? Well, for this case, we have a model like this. Y2 is our endogenous variable we want to deal with. Z1 is all exogenous variables in the model. And U1 is the arrow turn. For this case, the Y2 can also be written as an indicator function of Z delta 2 plus V2. The V2 is the arrow turn in the endogenous variable function. And the two arrow turns of U1 and V2 is independent of Z and follows a bivariate normal distribution, which has mean of 0, variance of 1, and a covariance of low 1. If you use this data, you can use the probit command to estimate this model and obtain all parameter estimates directly. Here's a warning. You should not try to emulate two-stage least squares as follows. First, to run the probit of y2 on z and obtain the fitted probabilities phi2 hat, and then run the probit regression of y1 on phi2 hat and the z1. Actually, the coefficients are usually much larger than other coefficients because phi2 hat has a smaller range than y2. And as far as we know, this forbidden regression estimates nothing interesting, although APEs have not been studied. To see why we cannot use the forbidden regression, we can write y2 as a phi of z delta 2 plus r2. This equation is what we have obtained from the first stage regression, and r2 is the error term. And then we can plug this equation into the original model and get this. And obviously, this equation is very different to what we want to estimate. And also, the alpha 1 r2 plus u1 is not independent of z and is clearly not normally distributed. This will also cause an inconsistent estimator for your probit regression. So, do not use the forbidden regression anymore. Let's study another example, which is the effects of children on labor force participation. And our main dependent variable is work or not. And our endogenous variable is the more kids, which is the dummy for having more than 2 children. And our population is women with at least 2 children. Here's our main regression model. In this model, we have the independent variable of more kids, non-wife income, women's education, women's age, age square, black people dummy, and Hispanic people dummy. And here we start with a linear IV, and the binary variable same sex is the IV for more kids. Because parents are likely to diversify their kids' sex, so parents with same-sex children tend to have more kids. So this variable will be a valid IV. We first test the relevance condition of our IV by regressing the more kids on the same sex and other exogenous variables. And the estimation results are as follows. As you can see, the same sex variable is positive and significant, which suggests that the same sex satisfies the relevance condition. It also suggests that more kids has an endogeneity problem. And next, we use the IVREG with our instrumental variable same sex to get a linear approximation to probit or logit model. Now we use biprobit to estimate model with binary endogenous variable more kids. Note that the first equation is the original model includes the endogenous variable more kids. And the second equation is the endogenous variable equation with the IV same sex and other independent variables. And estimation results are as follows. Please note that the first set of equation is our main results, which have eliminated the endogeneity of more kids by jointly estimating the original model and the endogenous variable models. Let's now see what if we use the forbidden regression. First, we estimate a probit regression of more kids on the IV same sex and other independent variables. And then we estimate a fitted probability called the phi2 hat. And then we regress the work variable on phi2 hat and other independent variables. And the estimation results are as follows. Please note that the phi2 hat variable has a coefficient of minus 0.84, which is quite a bit larger than more kids' coefficient in the bivariate probit estimation. However, these estimates are not robust and inconsistent. So please do not use the forbidden regression in your future study. If our dataset is panel format, we might encounter an unobservable effect problem. For this case, we have the model like this: the g of x beta plus ci. Ci is the unobservable effects, and this term do not change over time. If you calculate the partial effect by taking derivative with respect to xtj, then you can get this term. And obviously this term depends not only on the value of the covariance xt, but also on the value of the unobservable heterogeneity c. What about the partial effect if xt is discrete? Well, this is the difference between the two g functions of xt beta plus c, and the changes from the 0 to 1. And obviously, this term depends on c. But for any two continuous covariates, the ratio of partial effects is the ratio of coefficient beta j over beta h, because the two distribution functions are cancelled out in the calculation. So the ratio does not depend on the covariates or unobservable heterogeneity Ci. But however, what we are interested in is the magnitude of partial effects, not the ratio of the two coefficients, beta j over beta h. So how do we account for unobservable C? If we know enough about the distribution of Ci, then we can insert meaningful values for C. For example, if we know the mean value of Ci is equal to mu C, then we can plug this term into the PEA function like this. And also, we can obtain the APE by averaging across the distribution of Ci, like this. So if we know the distribution of Ci, then estimate APE is very easy just by averaging across Ci. But however, in practical, the distribution of Ci is unknown, and this will cause problem in the modeling of an observable effect. Generally stated, the key random effect assumption is that d of Ci given xi1 to xit equal to d of Ci. The d denotes some distribution function. But this assumption implies that the covariance between the xit and the Ci is equal to 0. But this assumption is very restrictive, because it implies that all APEs can be obtained by just estimating the expected value of yit given xit equal to xt. And in Stata, the xt probit or xt logit with an RE qualifier can estimate the random effects model. And generally speaking, including a set of time dummies is a good idea, and time constant variables can be included directly. We can also estimate beta without restricting d of Ci given xi, which implies that the correlation between c and x can be any functional form. This is often called the fixed effects logic, but it is really a conditional MLE on xit and Ci. And in Stata, the xt logic with FE option can estimate the fixed effects logic model. It is a natural question to ask when to use random or fixed effects model. Well, actually, it depends on the test results. There are two tests we can use. The first one is the Hausman test, which compares the coefficients on the time-varying explanatory variables and compute the chi-squared statistics. And the null hypothesis of Hausman test is that there is no systematic difference in coefficients between random effect and a fixed effect. If it rejects the null hypothesis, the fixed effect model should be used. And the second test is the variable addition test. But first, let a WIT be a 1 by j vector. The WIT is some time-varying factor in observable effects Ci, and then use the correlated random effects CRE formulation proposed by Monolac 1978. In this case, the CI can be decomposed into the psi plus wi bar c plus ai. A wi bar is the mean value of wit, which can be regarded as a long-term component of unobservable effect CI. This setting allows the CI to be correlated with the time-varying explanatory variables through its average level over time. And then we can substitute this term into our original model and get this. And we can estimate this model using the random effect model and test the null hypothesis that the C equal to 0. If it rejects the null hypothesis, then the CI has correlation with time-varying independent variables. Therefore, the fixed effect model should be used. Again, we use the merit-women's labor force participation data, but now it's a panel data set. The dependent variable is LFP, which denotes the inner labor force. We have a set of independent variables. The KIDS is the number of children less than 18 years old. LHINC is the logarithm of husband's monthly income. EDUC is the years of schooling. Black is the black people dummy. Age is women's age in years. AGSQ is the square value of age. The PR1 to PR5 are time dummy variables. First, we run the fixed effects regression of LFP on kids, LHINC, and the PR2 to PR5. Because we have 5 time dummy variables, so we can put only 4 of them. And then we store the estimated coefficients as BFE. And then we run the random effects regression with the same model setting, and also store the estimated coefficients as BRE. So here we are conducting the Hausman test. Please note that we use the sigma more command to tell Stata to use the same variance estimate, which will solve the wrong degrees of freedom problem in the Hausman test. The null hypothesis is that the difference in coefficients is not systematic, and the chi-square statistic is 9.04 with the p-value of 0.01. So this rejects the null hypothesis. Therefore, the fixed effect model should be used. Next, we conducting the variable addition test. The first step, we generate the mean values of kids and LHINC, the 2 time-varying variables, and save them as the kids bar and LHINC bar. And then we run the XT probit regression of LFP on a set of independent variables as well as the 2 mean variables. And finally, we jointly test the 2 mean variables, and the test results rejects the null hypothesis. So it implies that the unobservable effects is correlated with the time-varying explanatory variable. Therefore, the fixed effects model should be used. Next, I will present 3 papers that use linear probability model, probit, and logit model to show you how prevalent these models are in financial studies. The first paper is written by Deng Kang et al., the 2013 JV paper. The research question is that how does corporate social responsibility affect stakeholder value from mergers? In the past studies, there are 2 opposing views for the CSR. The positive view is called the stakeholder value maximization view, which states that the firm that's focusing on the interests of other stakeholders increases their willingness to support a firm's operation, which increases shareholder wealth. And the negative view is called the shareholder expense view, which states that managers engage in socially responsible activities to help other stakeholders at the expense of shareholders. And the authors collect the CSR score from KOD database. They also use two instrumental variables for the CSR score to deal with the omitted variable problem. The first instrumental variable is called the religion rank, which is the ratio of the number of religious adherents in the acquired state to the total population in 2000. This value is between 1 and 50. The second instrumental variable is the blue, which is equal to 1 if a firm's headquarters is located in the blue, that is democratic state, and 0 otherwise. The authors use the data of 870 successful and unsuccessful US mergers. This table shows the probit regression results of the effect of CSR on the successful rate of mergers. In the first two columns of this table, as you can see, the adjusted CSR score are positively correlated with successful mergers. In the column 3 to column 6, the authors use the two-stage probit regression to deal with omitted variable problem. In the first stage, they run the regression of CSR on two instrumental variables and get a fit value of CSR. In the second stage, they run the regression of mergers on the fit value of CSR and get the final results. Please note that the CSR score is continuous, so the two-stage setting can be used. As you can see in the column 4 and column 6, the adjusted CSR score are positively correlated to the successful mergers. So these results support the stakeholder value maximization view, which predicts that the mergers proposed by socially responsible acquirers have a higher likelihood of being completed. In the lower part of the same table, the authors also conduct a Craig and Donald test and an over-identification test. P-values for the Craig and Donald test are less than 0.001, which rejects the null hypothesis that the instruments are weak. So their two instrumental variables are valid. However, the p-values for the Sargent-Hansen test are less than 0.001, which rejects the null hypothesis that the two instrumental variables satisfy the exogeneity requirement. So there are two instrumental variables do not pass the over-identification test in the two-stage probit regression. The second paper is written by Phil and McChian, 2017 JFE paper. The research question is that how does director experience affect acquisition performance? In the past study, there are two hypotheses. The first one is the experience hypothesis, which states that the acquisition experience alone affects future acquisition outcomes. That is, firms with higher levels of board acquisition experience will engage in better performing acquisitions. At this point of view, only directors' experience can affect acquisition outcome. The second one is the performance hypothesis, which states that beyond experience, ability affects future acquisition outcome. That is, firms in which directors' prior acquisitions earn higher announcement returns will engage in better performing acquisitions. At this point of view, ability is another important factor of acquisition outcome. The authors used the data of 1,766 acquisitions completed by 993 firms from January 1st, 1998 through December 31st, 2014. They collected data from the Thomson Wines Mergers and Acquisition database. The authors defined two experience measures. The first measure is called the total number of prior acquisition, which is defined as the summation of NA. The NA is the total number of acquisitions in which Director I has participated outside the principal firm over the past 10 years. And the D is the number of independent directors on the board of the principal firm. The second measure is called the percent with acquisition experience, which is defined as the summation of A over D. A is an indicator variable which equals 1 if an independent director I has participating at least one acquisition outside the principal firm in the past 10 years, and 0 otherwise. The authors use the logit regression to test whether experience and ability can prevent large loss acquisitions in the future. The dependent variable is the large loss acquisition. This is a binary variable which equals 1 if the acquisition generated a loss of over $500 million. And as you can see in the column 1 and column 2 of this table, the total number of prior acquisitions and the percent with acquisition experience have no effect on the large loss acquisitions. But however, if the author used the number of prior acquisitions with positive CAR and the percent with positive total CAR, then the coefficient becomes negative insignificant, which implies that a director's ability can help firms to prevent bad acquisitions in the future. So the authors conclude that the quality of director's prior experience, not the experience itself, is important in helping firms to avoid large loss acquisitions. The third paper is written by Bernal, Bhagwat, and Rao in 2017 JF paper. The research questions that whether the intensity of early life experiences has a non-monotonic, that is a non-linear, impact on CEOs' attitudes toward risk, and thus on the corporate policies that they influence. To be specific, the authors hypothesize that CEOs' fatal disaster experiences in the early years may have an effect on their risk preferences and corporate policies. What they want to do is to find a causal impact. The authors also define several types of early life disasters, such as earthquake, hurricane, severe weather, urban fire, volcano, the weather, such as the floods, thunderstorms, hail, and wildfire. The severity of disasters is measured by the fatalities per capita in each of disaster. The disaster should occur in the CEO's county of birth starting 5 years and ending 15 years after the CEO's year of birth. The 15th year is the stopping time of one's early memory, according to some psychology literature. The authors group all CEOs into 3 categories of experience. The first group is the extreme fatality experience, which is an indicator variable equal to 1 for CEOs who are in the top decile for a number of disaster-related fatalities per capita experience in their birth county, and 0 otherwise. The second group is the median fatality experience group, which is an indicator variable equal to 1 for CEOs who experience some disaster-related fatalities in their birth county, but are not in the extreme fatality experience group, and 0 otherwise. The third group is no fatality experience group, which is an indicator variable equal to 1 for CEOs who experience no disaster-related fatalities in their birth county, and 0 otherwise. The panel C of this table shows the top 10 CEO birth states and the disaster experience. As you can see, the most CEOs are born in New York. And among the CEOs that are born in New York, the 27% of CEOs do not have any fatality experience. The 61% of CEOs have median fatality experience, and 11% of CEOs have extreme fatality experience. So there is a considerable variation in the disaster experiences of CEOs from the same birth state. In this table, the authors run the linear probability model of announced acquisition on disaster experience groups. The acquisition is a good proxy for risk-taking behavior, because corporate acquisitions are inherently riskier than other activities. As you can see, the median fatality experience group has positive impact on announced acquisition. which implies that the CEO who have a medium fatality experience becomes more aggressive. However, for the extreme fatality experience group, the impact becomes negative. That implies that the CEO who have the extreme fatality experience become more conservative. So the CEOs who experience fatal disaster without extreme consequences desensitizes CEOs to the negative consequences of risk. However, the CEOs who experience extreme fatal disasters and witness the downside potential of risky situations appear to be more cautious in approaching risk. So the authors conclude that there is an inverse U-shaped relation between fatal disaster experience and corporate acquisitiveness. After reviewing the three papers, we know that the linear probability model, probit, and logit models are widely used in financial studies, as these models are all valid methods. The linear probability model is quite a good linear approximation to the probit or logit model. You should also need to make sure to correct any heteroscedasticity, endogeneity, and unobservable effects to obtain consistent and efficient estimates as well as standard errors. And also you should not use any forbidden regression in your future studies. You should also conduct a test to find out which model, the random effects or fixed effects, is suitable for your data. Thanks for listening.